So today we are going to start the nanotechnology in chemical engineering. So we'll discuss about the properties of the materials that will prepares in nanoscales or nanomaterials. So one of the property that is the heat transfer, that is the very important property from chemical engineering point of view. So that is the thermal property, or you can say, so that is thermal conductivity, heat capacity, that will discuss. That is one of the physical property of the nanomaterials. So in our previous class we have discussed about the surface area, melting point and its catalytic property, that how that is changes when we convert a bulk crystalline materials into nanocrystalline materials. So today we will discuss the thermal conductivity or heat transfer property of that materials. Okay, so the thermal property means here thermal conductivity. So nanomaterials, when we convert a materials that is initially we have a bulk materials that we convert into nanocrystalline materials, nanomaterials. So the thermal conductivity of that materials will changes, and that will directly indirectly means effect on the heat transfer property of that materials when that we are using as a to resist the heats or supplied or heat dissipations, or to supply more amount of the heat or energy, heat energy from one point to the another point. So that would help us. Okay, so that would affect overall in the system performance. So here's what is heat transfer, that basic things we will discuss, and then about the thermal conductivity we will discuss. Heat transfer, that is the important process that occurs in many naturals or industrial process, means where heat transfer equipments we are using. So this unit operations is exist, and there is some transferring medium is there, so that carry the heat from one point to the another point. By that way we can heat up or cool down say systems. So in that particular process, heat transfer, there are different way that mode of heat transfer is there: conductions, convections and radiations. So these are the three different modes of heat transfer is there, and that can be applicable, as I said, from chemical engineering point of view, chemical plants. So where heat exchangers, there we can use as a heat transfer operations is there, pump, refrigerators and many more apparatus or equipments are there where heat conductions is very important. So if we develop say materials or systems having better heat conductions, that would transfer heats more efficiently and better way. Okay, so these are the three different mode of transfer, that is conduction, convection and radiations. So suppose you have a nanoplates, that what is nanoplates, that we will discuss, that acts as a medium to transfer heat from one point to the another points I said. So if we means when there is a two different mode of conductions or convections, radiations, mode of heat transfer. So here initially conductions, that is when transfer of heat from solid having one particular point to the another points, there is temperature differential gradient is there transferring heat. And in convections, when heat transfers medium is there, that may be liquid medium, so that carrying the heat from one particular point to the another particular point. So here when it is conduct means heat transfer in terms of conductions is coming. So then the important parameter that is called thermal conductivity, that is expressed in terms of small k, and it has unit watt per meter Kelvin. So that is the units. And when it is convection heat transfers, that is expressed in terms of convective heat transfer coefficient. So it has units watt per meter square Kelvins. So here this is the relationships H and K this way, or you can say K by delta, that is the film thickness or the distance within that heat transfer operations or film thickness you can say. So here various medium, so where heat transfers we can say that means possibilities there in gas, liquids or solid phase in different places where you can see that heat transfer operations may be there. As a result, the thermal conductivity or that particular systems or phase, if it is gas, so then thermal conductivity is very low. When it is liquids, that thermal conductivity is also little bit higher than a gas, and when it is solids, the thermal conductivity is extremely high. So from gas to liquid to solids if you move, so then thermal conductivity of the materials will increase. As a result, rate of heat transfer will enhance. Okay. So the thermal conductivity, how we can express the key or the thermal conductivity rate of heat transfers. I said the thermal conductivity of a materials, that is defined by rate of transfer of heat per unit times per unit cross sections area per unit temperature gradients. Okay. So, this is the rate of heat transfer per unit time, this is the temperature gradient delta T by delta x, this is area. So, thermal conductivity K is expressed in terms of Q by T delta T by delta x, and A is the surface area. So, per unit area what would be the rate of transfer of heat, that if you want to know or measures, if suppose materials we have prepared having a high thermal conductivity, means rate of heat transfer would be more. So, therefore, this is the mathematical expressions how we can express that thermal conductivity. Okay. So, now this whens means here we are studying the nanotechnology. So, means when we are dealing with a materials that is having a bulk size and that we are converting into nano. Okay. So, when we are converting bulk materials into nanomaterials, means overall surface area, other things that would changes, means size of that materials we are changing from bulk to nano. So, that would affect overall thermal properties of that materials or thermal conductivity of the materials. So, then overall system property will changes, systems much more would be depending upon the applications that would affect on that particular systems. Okay. So, here is how experimentally we can find out the slope that is equals to thermal conductivity, that is showing here. See here heat capacity, that we will discuss later. So, now the different factors that affecting the thermal conductivity of the materials, that components we will discuss. So, factors means when we converted that materials bulk to nanomaterials, the thermal conductivity I said that would be higher and than the bulk materials. Therefore, when it is higher value, then the heat transfer would be much more better. Okay. So, in bulk material it is relatively large size of that materials, and in case of the nanomaterials the surface area to volumes ratio that will change or increase. So, that would means changes the overall performance of the systems. So, once we converted a bulk material into nanomaterials, I said that overall surface to volume would changes. So, then means materials whatever we are using, the size of that materials or nanomaterials that would influence the phonon. So, phonons means that is the mean free path or lattice vibrations that would change. Okay. Therefore, that would affect overall thermal conductivity of that materials. Okay. So, as the materials converted into nanoscales reduce their mean free path, and then that would reduce the thermal conductivity of that materials. So, when we changes from bulk material to the nanomaterials, so then the mean free path of that individuals molecules one to another, so then that would decrease. As a result, the thermal conductivity also will decrease. So, another is surface interactions. So, when particular surface that is in attached or contact with the airs or others fluids or materials, that would also affect overall heat transfers, means surface interactions, interaction between the surface of the nanomaterials and the surroundings systems or environments, that may be air, water, whatever the materials or solid material that is present, that would affect the overall heat transfer. Okay. This I said also that phonon or surface scattering, that is the phonons, what is that is the quanta of lattice vibrations that carry heats. So, when materials converted into nanomaterials, so I said that mean free path that will decrease, as a result decreasing the thermal conductivity. So, that would depending upon the applications. If we changes that bulk to nanomaterials, so if somewhere we need to lower the thermal conductivity, so then that would help. Okay. Next is the shape and orientations. So, we can convert a bulk material into nano. So, it has a particular shapes or orientations also, that may be spherical shapes, cubical shapes or cylindrical shapes. Depending upon that particular shapes or orientations, that also influence the thermal conductivity. So, the thermal conductivity we are interested, so that would also affect the shape and orientations of the material. So, here we will show a few examples. So, where this particular nanomaterials that will use or applications is there, so where means if we convert bulk into nanomaterials, so then that would affect, let us say heat sinks. So, where the materials with the high thermal conductivity, that we can use materials having high thermal conductivity. So, that what would help, that efficiently dissipate the heat. Suppose we have a electronic device where heat formations or heat generations is there. So if we develop some materials that means remove or dissipate heat from that surface very fast, efficiently, then that materials we can choose for that particular device. So then that device performance will be better. Okay. So we have to choose materials that having high thermal conductivity. So instead of having materials lower thermal conductivity, sometimes material is better than nanomaterials. Depending upon that applications, we have to choose whether the materials up to what particular size or shape dimensions we have to use to get a better performance depending upon that applications. Energy storage device, if we use that nanomaterials in energy storage device, so there's when energy storage means heat energy that we want to thermal energy that want to store in that particular systems or device. So there's the materials you have to choose or you have to select such a way that that materials having either depending upon that maybe higher good thermal conductivity. So that tunable thermal conductivity means that way depending upon the application. So we can choose that materials or we can select that materials. Next is the nanofluid application. So here suppose in any heat transfer equipments, heat exchangers, we use fluid. So there's fluid, that is the medium that we have to use to dissipate or transfer of heat from one particular phase or particular state to the another state or phase. So then the fluid we are using, most of the heat exchangers we use water as a base fluids or fluids that we usually use. So for a particular heat exchanger equipment, so using only waters or as a fluid, the performance will get that particular device. Instead of that, if we use nanofluids, nanofluid means with that fluids, if we use nanomaterials and make that fluids, that would gives better performance. Means that fluids having thermal conductivity of waters, and whence it is mixed with nanomaterials or nanofluids, then thermal conductivity will enhance. As a result, that performance of the device will be better. So that we can see. So here's what are the various nanomaterials we can use to improve the thermal conductivity of for that particular device. There are so many nanomaterials I discussed in my previous class also. So graphenes, carbon nanotubes, many nanomaterials, metal oxides materials are present, so that we can use that having high thermal conductivity that may be suitable for heat dissipations or heat transfer applications. Nanofluids that we can use that helps in disperse the nanoparticles, means we can use or disperse in a fluid, particular fluid. So that would enhance the thermal conductivity of that fluids that we have set or initially we are using. So we can improve that. Similarly, metal nanoparticles that also we can use to improve the thermal conductivity of that particular composite or that particular materials, where metal nanoparticles may be much more suitable to improve or enhance the thermal conductivity of that systems. Here one just example I am showing. So heat exchanger, that is very common in for heat exchange in any chemical plants. So there's nanomaterials we can use, that nano fluids that we would be passed through this device to enhance the thermal conductivity or heat transfer performance. So here's a list of metal nanoparticles I am showing here. Let's say graphenes, it has thermal conductivity at room temperatures is extremely high, 3000 watt per meter kelvins. If we look into the carbon, multiple carbon nanotubes, it has high thermal conductivity 2000, nano diamonds thousands, and metals that having 429, and different metal oxides, metals also that also having the thermal conductivity. But graphene, multiple carbon nanotubes, those materials having extremely high thermal conductivity. So those materials are very good, means materials that can be used when suppose a particular base fluids we are using. So let's say here's so many base fluids that we are showing here. Let's say base fluids is water that may be used for the heat exchanger I said here. Instead of nanofluids we can use water also here. So once we use water, we get a particular thermal conductivity that water having, and depending upon that we can get a particular rate of heat transfer. So, when we use some nanomaterials that mixed up with the base plates at particular concentrations, the concentrations of base nanomaterials is very important. So, a particular concentrations if you use, and so that is applications is heat exchangers, cell and tube type of heat exchangers. So, there's it has been observed or reported that the thermal conductivity will be increased approximate 30%. Okay. So, that is the one examples. Like that many nanomaterials we can use with the base plates for a particular application, plate types, fin types or any other heat exchanger device. So, there's that materials will enhance the thermal conductivity of that particular fluids and enhance the heat transfer performance. Here nanoplates how we can prepare, that I am showing here, graphene oxide synthesis and nanoplate preparations, and later we will discuss more details. So, here's one experimental results I am going to show. So, effect of nanomaterials, that is CNT to as a nanoplates, CNT used as in nanoplates. So, base plate is water, you can see the thermal conductivity is this y axis. So, is that much, and whence the concentration of CNT gradually increased, the thermal conductivity also increased. Okay. So, here's different metal oxides also we can use as a to increase the thermal conductivity with the base plates. So, here base plate is water, you can see that is the thermal conductivity is very low. Okay. Whence we are using Fe3O4 with the base plates, the thermal conductivity jump to this. Okay. Similarly, others also is there with respect to the base plates, the thermal conductivity of copper when we are using with the base plates, the thermal conductivity changes. Okay. So, depending upon a particular nanomaterials that we are using with the base plates, the thermal conductivity of the systems as well as the performance of the systems will enhance or increase. Okay. So, different here I am showing a CNT type of nanomaterials, carbon nanotubes. So, here's metal oxides I am showing as a nanoparticle, and here's the shape and orientation of that materials. I said shape of that nanomaterial is very important. So, same the material consists of the same materials, but its shape is different. Suppose you have developed a nanoplates, that is titania water, TiO2 water, that is our nanoplates. Okay, nanoplates. So, that we have developed. So, here base plate is water and titania is the nanomaterials. That titania we can make cubical or rod type or spherical type of titania we can develop. So, the materials consist of same components titania, but shape is different, one is cubical rod type or one is spherical types. So, it has been observed that when it is base plate is water, so that thermal conductivity is here. Okay. So, when we are adding titania with that, the thermal conductivity of course will enhanced. But when we are using cubical shapes of titania, the thermal conductivity is highest as compared to the other type of means rod like or spherical shape of that titanium. So, both the here also TiO2 water, here also TiO2 water, here also TiO2 plus water, but when it is shape is cubical shape, that would give much more better performance in terms of thermal conductivity. Okay. So, cubical shapes possess the highest thermal conductivity and spherical type of nanomaterial that would give the lowest thermal conductivity. So, therefore, the performance of the device should be different. Okay. So, next is the heat capacity or specific heat capacity. So, specific heat capacity is expressed in terms of Cp and heat capacity is C. Okay. So, specific heat capacity, Cp is the specific heat capacity. So, M into Cp is the specific heat capacity and Cp is the specific heat capacity. So, both are same, but there is one is multiplied with molecules weight of that materials that we are using. Okay. So, heat capacity is expressed usually this way. So, this is also thermal property or particular materials or fluids whatever we are considering. So, that is huge whence the total amount of the heat that we are transferring from one systems, that is expressed Q. Q is the total amount of the heat that is transferred, that if you want to calculate depending upon the nanofluids are using. So, heat capacity also changes. So once the heat capacity means when suppose we have a base fluids and that has a particular heat capacity or specific heat capacity, and in that base fluids if we use a particular nanomaterials, so then base fluid property would change, means the specific heat capacity that fluids will change, as a result total rate of transfer of heat that would change. Here when the materials, let us say silver bulk and nano we can use, here bulk silver particles, here silver nanoparticles. So if we use bulk silver, so then space heat capacity C is like this, that way it would change. Okay. When silver nanoparticles means is used, then the heat capacity of that fluids will change. Okay, so that will enhance. So similarly if we use copper nanoparticles, bulk copper, so then heat capacity of bulk copper is following these lines. Hence we are using a particular diameters, that may be 6 nanometers or 8.5 nanometers of copper we are using, so it would change the heat capacity of that particular systems or fluids. So then the overall rate of transfer of heat will change. So specific heat is changed or increased as reduce the size of the metals from bulks to the nanomaterial. So if we convert a bulk materials into nanomaterials, and that we use for a particular systems where specific heat, that is our study of interest, then specific heat will increase as we reduce the size of the materials. Okay. So here few examples are there also, means you can see. So where if we increase means suppose here we have a ceramics, that is non-conducting, metal is the conducting. So if we use nanomaterials in ceramics, then thermal conductivity will increase, or that would non-conducting to conducting property that will develop. Suppose you have a metals that is that has conducting properties, if we use some nanomaterials in with that metals, then the metallic property of that particular metals will change. Okay. So here borons is non-metals, we can change into metallic property or we can develop in that. So one two examples I will show. So how the nanomaterials will affect the that property, means the nanomaterials enhance or increase the conductivity of the ceramic materials. Suppose you have a ceramic materials, we add their nanomaterials, that would increase the conductivity of that ceramic. Okay. So here transforming conducting materials into semiconductors, means here suppose we have a initially ceramics, so there we are using nanomaterials. So then initially it was non-conducting, so then when we added nanomaterials, that non-conducting to conducting property that will develop in ceramics. Similarly when we are using metals, in metals we are adding a certain portion of nanomaterials that would increase the electric resistance of that metals. So then what would happens, that metals would be semiconductors or insulator type of property that would be develops in that metals, means metals would be converted into either semiconductor or insulating type of materials. Okay. So when we are using nanoscales of nanomaterials, the electronic property I said that would change from nano to bulk when we are changing. So suppose we have a borons, boron, that elements that we are using for a particular electronic device, it is non-metals, borons basically. Whence we adding some nanomaterials with that, so then borons or borophins we are forming, means that borons we converted into the borophins that appear are excellent or acts as a two dimensional metallic properties. So initially boron was non-metals, whence borons, as a borons we are using, and borons converted into borophins, that would gives or show some metallic property. Okay. So here's different nanoparticles, metallic, carbon based metal oxides and other type of magnetic, non-magnetic carbons, different type of materials that we have discussed in your previous class also. So how the nanofluids we can develop, and what are the basic mechanisms, how the thermal conductivity of that material. Suppose you have a fluids, there we are adding nanomaterials to make nanofluids. how the thermal conductivity of that nanoplates will change by adding or additions of nanoparticles in that systems. So, whence we are adding nanoparticles and to develop say nanoplates that increase the Brownian motions, aggregations and formations of an orderly liquid layer around the nanoparticle that play a significant roles in the nanoplates thermal conductivity enhancements. Okay. So, I said whence this is base plates and here we are adding nanomaterials that would be distributed in that plates that developed and that we get nanoplates. So, once we adding that nanomaterials in that plates, so there is a Brownian motions, aggregations or any other things means layer formations that would helps in enhancing or increasing the thermal conductivity of the system. So, here you can see a nanoparticles that is present in a plates or nanoplates. So, there's surroundings or outside of that materials formations of nano layers, that means it is a theory layer models that is discussed in here. So, you can see that. So, a interfacial layers formations is there, that layers acts as a thermal bridge between two solid nanoparticles. As a result, the thermal conductivity of that nanoplates will enhanced or increased. Okay. So, here is one nanoparticles, here is one nanoparticles, into bridge two nanoparticles there is nano layer formations is there that I said. So, that acts as a bridge in between two nanoparticles whenever heat transfer is required from this point to this point. So, then imaginary nano layer formation is there and that would enhance the thermal conductivity of the plates. As a result, overall rate of heat transfer will enhance. Okay, that would give the better performance of that systems heat transfer equipments. Okay. Next is the aggregations models, means I said whence nanoparticles is present in a particular fluids that would move randomly, that is called Brownian motions. Okay. So, whence nanoparticles is there that would reduce the Brownian motions in that particular fluids due to the aggregations. So, when single nanoparticle is there that is moves very freely here and there, but when lot of or 2 or 3 nanoparticles agglomerates aggregations is there, then the Brownian movements would be reduced. Cluster formations is there in the nanofluids where the nanoparticle is suspended, that also one way leads to the means suspension, means clusters or nanoparticles that would be stables in the nanofluids that is suspended, that also means assist in settling, means when individual nanoparticles is present that mere possibility is the settling or depositions is there, then fluid property will change, that we will discuss later also. Okay. So, when cluster formation is there, the cluster reduce the stability of the nanofluid suspensions and lead to the nanoparticle settlings. Okay. So, however, nanoparticle clusters increase the contact in between nanoparticles. So, if nanoparticle cluster formation is there, so this type of cluster formations is there or aggregation due to the aggregations that will increase the contact between nanoparticles and increase the thermal conductivity of that system. So, that is another theory that is also proposed. So, these are the things we have discussed. Thank you.